Hello everyone, my name is Alireza Erfanian and I'm happy to present our paper entitled Lightweight Transcoding at the Edge for Live Streaming or LwTE-Live on behalf of my colleagues at the University of the Klagenfurt. The agenda of my presentation is the introduction of the live streaming application at the first, then we elaborate the proposed approach and talk about the result and have a conclusion on future work and the Q&A at the end. As you know, live streaming is a specific type of streaming that the media is broadcasted in real time. This type of streaming is suitable for the live venue like the concert, sports venue, award show, conferences, educational events, and so on. Live streaming application has experienced a significant growth in the recent years and is expected to have a more booming days in. But there are two main challenges confronting with the live streaming. The first one is end-to-end latency, that is a crucial key parameters that is conflicting with the other key parameters like the video quality and low rebuffering ratio. The other one is the scalability, especially for the popular event that many clients want to join to the live streaming channel. That leads to congestion in the network and undesirable performance and consequently perceived queue at the client side. For example, as you can see in the fig reported by the British Telecom during a football match, the demand for the bandwidth in the backhaul of the network is almost doubled. Uh, the conventional live streaming workflow consists of three phases. In the ingest phase, the video is captured and then uploaded to the AVR encoder and then provided in different resolution and quality called representation set or the bitrate ladder. Then it's offered to the clients in a media description file or MPD. The clients, based on the predicted network situation and client's characteristic like the buffer status, select the appropriate representation and request it from the origin server. And the origin server delivered the requested representations to the client through the CDN servers. It's obvious this approach that's widely used in the industry introduce high bandwidth utilization, especially in the between the clients and the CDN servers. The other, by emerging the edge computing paradigm, it's possible to use the processing and the storage capacity at the edge server to run some network functionality at the network. One of this network functionality that we can run is the virtual reverse proxy. By using virtual reverse proxy, we can collect the client's requests at the edge of the servers and then uh, aggregate them and only request uh, only fetch the requested bitrate one time from the CDN or the origin server. Using this approach can decrease the backhaul of the network utilization. But in the other hand, it may introduce a higher end-to-end latency due to aggregation process at the edge server. We also can employ the transcoding We also can employ the processing power at the edge server to perform the transcoding at the edge server. By using this approach, we need only to fetch only the highest requested representation from the origin or CDN server and then prepare the other requested bitrate or representation at the edge server. Using this approach can decrease the more backhaul network utilization. But in the other hand, it introduces a higher end-to-end latency because the transcoding operation is a computation intensive and time consuming process. Uh, in our previous work to solve this problem, we proposed a novel lightweight transcoding method at the edge or LwTE called LwTE that reduce the transcoding time at the edge up to 80% compared with the conventional transcoding method. The main idea of LWT is to extract some features during the encoding process at the edge server in the origin server and reuse them in the transcoding process at the edge server to reduce the transcoding time and consequently the computation cost. Considering a simple example that clients connected to the CDN or origin server through an edge server equipped with the 40 CPU core and 200 megabit per second connection between the edge server and the origin or the CDN server. Moreover, assume that the client's requested representation R1 to R5, that R5 has the highest quality and the highest bitrate, and the R5 has the lowest quality and lowest bitrate. The table B showed the transcoding time of the representation 2 to representation 5 from the representation 1 in different instances in terms of the CPU core. And the table C showed the bitrate of each representation and the corresponding metadata. The feasible solution for serving the clients at the edge server is depicted in the figure D. As you can see, serving all the incoming requests by fetching from the origin server results in the highest cost. The other feasible solution are showed also in this figure. You can see that by transcoding, by preparing the representation 3 and 4 by transcoding at the edge server and fetching the other representation, it means the representation 1, 2, and 5 from the origin server. With this combination, we can reach and we can achieve the minimum cost. So, by considering the resource limitation, including the bandwidth and the computation resource at the edge server, the question is how we can decrease the live streaming cost, including the computation and the backhaul cost, while increasing the scalability scalability of the live streaming by saving the network backhaul bandwidth and taking into account the following constraint. That is, the first is the bandwidth limitation between the edge and the origin server. the computation limitation at the edge server, and deliver and serve the client's request in a acceptable end-to-end latency. We we formulate this problem with the cost function of minimizing the computation cost and the bandwidth cost. With the three group of the constraint. In the first group of the constraint, we introduce the constraint called the serving policy constraint. We introduce the constraint that select an optimal policy, including the transcoding at the edge server or fetching from the origin or CDN server. The first constraint in this group selects an instance for request R if the transcoding policy has been selected for R. And the second constraint guarantees that at least one representation with higher bitrate than bitrate R must be downloaded from the origin or CDN server. This representation is needed for transcoding the representation R from it. The second group of the constraint called the serving time constraint guarantees to meet the given deadline for serving all requests. The first constraint in this group determines the total transcoding time when considering the available computation resource. The second one determines the total fetching time by taking into account the available bandwidths between the edge and the origin set. And the last constraint guarantees that the total transcoding time plus the total fetch time should be less than the given deadline. The third group of the constraint, called the computation resource constraint, determines the required computation resource for transcoding operation at the edge server. The first constraint in this group determines the required computation resource for performing the transcoding operations at the edge server. The second one guarantees that the largest selected instance does not exceed the available computation resource at the edge server, and the last one guarantees to provide the required computation resource during the transcoding time. We evaluate the proposed MBLP model through a 10-minute live streaming session. We also perform the transcoding operation on Amazon EC2 instances with various resource profiles in terms of the CPU and RAM. We also set the default value for the segment length, computation resource, and the bandwidth between the edge and the origin server to the 2-second, 16 CPU cores, and 100 megabit per second respectively. We compare the proposed MBLP model with the following state-of-the-art approach. The first one is the OSCAR that determines the optimal policy, including the fetch from the CDN or origin server and transcoding from a higher representation through by employing the conventional transcoding approach. The other one called fetch all does not perform any transcoding operation and served all incoming requests to the edge server by fetching from the origin or CDN server. In the first scenario, we evaluate the performance of the LWT in terms of the transcoding, time saving, and the relative bitrate of the metadata. As you can see in the left figure, we measured the saving transcoding time compared with the conventional transcoding time in different instance type in terms of the core CPU. As you can see, LWT could save the transcoding time up to 60% compared with the conventional transcoding time. By increasing the processing power, the saving transcoding time uh, is decreasing, while the LWTE is a lightweight transcoding process and is saturated very fast uh, in the instances with the 2 or at most 4 with the 2 or 4 CPU cores. But but in the other hand, the conventional method is a intensive computation process, and it take a lot of process here at these two instances to be saturated. So increasing the processing power is more beneficial for the conventional transcoding approach. In the right figure, we show the relative bitrate of the metadata compared with the corresponding representation. As you can see, the size of the metadata is relatively small compared with the corresponding representation. In continue, we evaluate the performance of the proposed model and compare it with the state-of-the-art approach in terms of the bandwidth utilization and the normalized cost. As you can see, LWTE could surpass the state-of-the-art approach and save the cost and the bandwidth utilization up to uh, 34 and 45% respectively. In the next scenario, we evaluate the performance of the LWTE and compare its performance with the state-of-the-art approach in terms of the normalized cost, bandwidth utilization, CPU utilization, and number of the transcoded representation for various bandwidth profiles from the 60 to 200 megabit per second. As you can see in the figure A and B, LWT achieved the best performance in all cases. However, by increasing the available bandwidth, the LWT and the normalized cost of the LWT and OSCAR are decreased. For the bandwidth utilization, by increasing the available bandwidth, we have by increasing the available bandwidth, the bandwidth utilization is decreased. Considering the number of the transcoded representation here, that is almost double for LWT compared with the OSCAR, the CPU utilization is CPU utilization values is reasonable compared with the OSCAR. In the last scenario, we evaluate the LwT performance and compare it with the state-of-the-art approach in the terms of the normalized cost, bandwidth utilization, CPU utilization, and number of transcoded representation for various segment lengths from 1 second to 4 seconds. Again, as you can see, LwT could achieve the best performance compared with the state-of-the-art approach. However, as you can see in the figure A and B, all approach has their highest cost and bandwidth utilization when we use the 1 second uh, 1 second segments. By increasing the segment length, the normalized cost and bandwidth utilization for all approach are decreased. This is because the overhead for each segment is constant, and by increasing the segment length, the ratio between the overhead to the segment data is decreased. We investigate the cost efficiency of the uh, LwT for live streaming application. We also formulate the problem of minimizing the live streaming cost by selecting the optimal policy, including the fetching from the CDNR origin server and transcoding from a higher representation to serve the incoming request to the edge server as a MBLP model, and compare the proposed method with the state-of-the-art approach in terms of the live streaming cost and backhaul network utilization. The results showed that the proposed approach could save the cost and backhaul network utilization up to 34 and 45% respectively. We are going to extend LwTE-Live to support multi-PEL video channel and also relaxing some assumption in this paper in the future work.